All right. So we're continuing with the spectroscopy series. I feel they keep pushing this to the wall. Oh, so all of a sudden I'm going to be here teaching. It's just this is too close. Okay. Continuing with the spectroscopy series. And last Monday, we talked about intro to spectroscopy. We gave general information. We even did the recap questions, thanks to Zach. And then, now we're moving on to more detail and talking specifically today about UV-Vis spectroscopy. All right. Which of the following is true? Let's see if you can at least guess. Have you heard of the term molar extinction? I'm sure you have. Have you heard of the term absorptivity? No? Okay, you're going to hear about it today. All right, then you wouldn't know if this is correct or incorrect. The first one. Anybody would like just to volunteer for a easy +2? Okay. B and C? C is absolutely wrong. But you wouldn't know that. Well, we're going to talk about this. And A is wrong. Every analyte has their own molar extinction or absorptivity. And this is the only correct answer. And we're going to talk about Beer's law. It's actually Beer's-Lambert, and two people that came up with the law. And I don't know why Lambert's name got dropped. It's only referred to as Beer's law, but it's Beer's-Lambert law. Anybody remembers Beer's law? Anybody heard of Beer's law? Yes, okay. You remember what it is? Or anything about it? It's basically the relationship between absorption and concentration. Absorption of light and concentration. And there is an equation. We'll show it in a minute. So B is the only correct answer, and we'll talk about all of them. We're going to talk about what's molar extinction versus how the concentrated sample may impact Beer's law, and the incident beam versus the exiting beam, how they differ. Okay. In both absorption and fluorescence spectroscopy, UV-Vis radiation is used. The transmitted beam is the signal measured. A grating monochromator is needed. Nick? Maybe A and C. Anybody else with a maybe answer? A guess answer? Okay. A and C is correct, but B is correct too. So in absorption or fluorescence, oh, actually not. Nick was correct. A and C, I just realized something. In absorption, this is correct. In fluorescence, it's not correct. Of course, you knew that, right? In fluorescence, you're not measuring transmitted beam. You're measuring the fluorescence that comes out of the, yeah. Okay. A and C is correct. We're going to talk about the grating monochromator more. We did mention it last time, when we were talking about HPLC, but I'll talk about it a little bit more here too. Okay. So, in UV-Vis spectroscopy, we always either measuring absorption or measuring fluorescence. And by measuring absorption or measuring fluorescence, we are looking for qualitative information or quantitative information. So qualitative, we are either looking at structural characteristics to identify, to detect, to do forensic work where we're looking for unknowns. For quantification, obviously we have standards, we're on calibration, we have standard curve, and we get quantification of compounds by linking absorption to concentration of known standards. Absorption or fluorescence. So absorption or fluorescence can be either inherent signal, that means either the compound itself can absorb light, like for example isoflavones, they can absorb UV light, or phenols in general can absorb light, whereas sometimes you have a constituent that does not absorb light, but you can measure it with spectroscopy if you induce a chemical reaction that will result in a product that can absorb or fluoresce. So an example of that is glucose. We will talk about glucose quantification in the carbohydrate, but an example of chemically induced is glucose does not absorb light, but we can react it in such a way to get a product that will absorb light. So we can use this technique for quantification of macro components like total carbohydrate. We're going to do this assay in the lab, phenol sulfuric assay method, and we're going to use spectroscopy to determine the concentration. Or we can do it for micro components like determining vitamins, like thiamine, fluorometric method, which is measuring fluorescence. We can use it in enzyme-linked immunoassays to determine allergens. So we have a lecture on enzyme-linked immunoassays. We're going to talk about how we link enzymes to antibodies. The antibodies interact with the allergen. Then we add a substrate, and the substrate is converted to a product by the enzyme, and the product absorbs light. And that is how we determine the presence of allergen. I'm going to break my neck doing this. I'm just going to look here. Okay, so determination is based on the measurement of the amount of light absorbed from a reference beam. So here we have, we call it the incident beam. So the incident beam is directed towards your sample, and the sample is present in a compartment. And you will be using these compartments in the lab, and we call them cuvettes. So the cuvette will have your sample in it, and the light is going to go in, and some of the light actually is going to be reflected back. Some of the light is going to be scattered. Some of the light is going to be absorbed, and the remainder of the light is going to be transmitted. So that's the exit beam. So that's your exit beam, that's your incident beam, and then here things happen. So the analyte in solution will affect how much light is transmitted, because some of the light is going to be absorbed. So the more absorption, the less transmitted light is going to be. So relative transmittance or absorption can be correlated to the concentration. So the higher the concentration, the higher is the absorption, the lower is the transmittance. But the relationship between concentration and transmission is not linear. However, the relationship between concentration and absorption is linear. And that's why we use absorption to determine concentration. We don't use transmittance to determine concentration. So the transmittance is basically a ratio of the transmitted light or the exit beam over the incident beam. And percent transmission is multiplied, that value multiplied by 100. Like I said, there is no linear relationship with concentration. And here it is, the fraction of the incident beam that is not transmitted does not equal the solution's absorption. Because we said some of the light is reflected back, some of the light is scattered, okay? So we cannot say P0 minus P equal absorbed light. Okay, Absorption is related to transmission, and this is the relationship. It's actually minus log T. And it does have a linear relationship with the concentration. And here is Beer's law, or Beer's-Lambert law. It defines the relationship between absorption and concentration. And here is the most famous equation of Beer's-Lambert law, which is absorption equal absorptivity multiplied by B, which is the distance the light travels. So if you have a cuvette, that would be the width of your cuvette. And C is your concentration. So if you know the absorptivity of your compound, which a lot of compounds already by experimentation, we know the absorptivity value of it, and we know the length, we can determine the concentration, even without a standard curve or running a standard curve. I think this is what I defined. So the concentration is in any concentration unit. So it can be molar, millimolar, milligrams per milliliter, percentage. Any of that is a concentration. Already said what the B is. That's the path the light travels in centimeters. And A is absorptivity, which has a unit per centimeter per concentration. That's why in this equation, all of the units cancel and absorption doesn't have really a unit. And A equal this molar, this, what do you call this shape? Sigma? No, well, no, is that sigma? Never mind, it has this I knew it, but now it's gone. Anyway, when units are in centimeter per centimeter and per molar as a concentration, then the A is referred to as molar absorptivity or molar extinction. It means the same thing. Okay? So when you hear molar extinction and when you hear molar absorptivity, they mean the same thing. And if you see molar, that means you are relating the concentration in molarity. Absorptivity is a proportionality constant dependent on. So it's a constant, and it depends on. Yes, Daniel. Ah, yes. Thank you. Okay. So yeah, back to this. Any guesses? Be alive. Evan. A and B. Well, A and B are correct. All of the above. Yes, because absorptivity is dependent on the lambda, the wavelength, because every compound will have a spectrum, remember? So they would absorb differently at different wavelengths. So when you're measuring at a particular wavelength, you have a particular absorptivity at that wavelength. Change the wavelength, you have a different absorption and different absorptivity. Molecular properties of the species obviously is what kind of structure it is. Does it have double bond? Does it have a phenolic structure? What's the absorbing functional group in that unit? And depending on the absorbing functional unit, it will have different absorptivity. A chemical environment, so is it acidic? Is it basic? Is it high in ionic strength? It will impact the ionization state of your compound, and thus it will absorb differently at different wavelengths. Therefore, it will have different absorptivity. So in quantitative absorption spectroscopy, we really want to accurately determine how much light is absorbed. So in order to do that, we always have a reference cell, or we call it a blank. Whoever worked in a lab and used a spectroscopy tool to quantitate would know that you always have to run a blank. And the blank could be as simple as water or a buffer or any reagent composition that your sample is dissolved in or is prepared in, to account for any interference or absorption by reagents, to account for scattering and reflection, so the scattering of light and the reflection of light. So you always run a blank to account for all of this, and we call this zeroing. So you put the blank and you zero the instrument, and then the transmitted light would be your emitted, or not emitted, your incident beam. When you correct for all of that, the transmitted light from the blank becomes your emission. Not emission. Incident beam. I'm tired. Okay. All right. So we have recap questions. Are these recap questions in your notes? Okay, great. We can come back to them. All right. Deviation from Beer's law. So there are certain instances where we cannot apply A equal ABC. So in these situations, so when the analyte concentration is greater than 10 millimolar, when you have relatively high concentration, your molecules are very close in space to each other. So the electrons on each molecule is going to be impacting the other electrons on the other molecule because of being very close in proximity. And when that happens, absorptivity is different, is impacted. Okay? So we cannot apply Beer's law when you have high concentration. That's why most of the times we dilute our samples quite a bit and then convert by using the dilution factor back to the original concentration. So chemical processes, that has to do with the environment and the ability of your molecules to ionize. So oftentimes we run our reaction in a buffered system to avoid ionization or change in the ionic form of your compounds, because some molecules has the ability to associate and dissociate, and that is impacted by the pH, impacted by the ionic strength. Therefore, if we control that, we avoid variations. If it's uncontrolled, we cannot follow Beer's law or utilize Beer's law. Polychromatic light, by definition, that means we do not have one wavelength. So the light has not been filtered into one particular wavelength. You have multiple wavelengths hitting your sample. You will have multiple absorptivity. So obviously the equation cannot be followed. You only have one absorptivity for the Beer's law to apply. Therefore, always when we're quantitating, we quantitate at a particular wavelength. We want to make sure that our instrument is providing that one particular wavelength for quantification. That's in quantitation. But if we're doing qualitative measurement and structural elucidation, we want to see a spectra, for example, then that is fine. But when we want to quantitate, we have to select one wavelength. Procedural considerations, so sample preparation. So always when you prepare a sample for measuring absorption, you want to make sure that the sample is homogeneous. So your solution is not separated into two phases. It's completely homogeneous and it's not cloudy. If it's cloudy, your absorption measurements are going to be really high. Why? Because there will be a lot of light scattering happening. So we don't want that. We want to make sure it's clear. So oftentimes what we do is when our solute or compound of interest, we know it is soluble, but there are impurities in there that we don't want, we centrifuge. So that means we clarify by centrifugation, get rid of the precipitate, and take our clear solution to measure absorption. So chemical modification, that means correct for modifying reagent. That means when you have the right blank. Your blank should be as close to your sample as possible without having your analyte in it. That will give you the most accurate quantification. If you have in your sample components that are not present in your blank or not present in your standard, you're not going to get accurate results, because some components in your sample preparation might either scatter light or absorb light as well in that region. So you want to make sure you correct for that by using the correct blank. This is very important, the sample holding cell, or in some cases you have a microplate reader, so you have a plate instead of a cuvette. So in this case, you want to make sure that your cuvette that you're using is compatible with the wavelength that you're measuring at. So for example, you don't want to use glass when you're measuring at UV. So under UV, glass absorbs the UV light. So you don't want that. So you want to use quartz or fused silica when we're measuring UV absorption. When we're measuring visible absorption, we can use glass, we can use plastic, which is even cheaper. So using the sample compartments is very important to decide on the sample compartment. And there are different types of cuvettes that you can get. You can see the regular cuvette size, which can take, what, 1.5 milliliters. But sometimes you don't have that much sample. Sometimes you are limited in your reaction. So you can purchase actually a cuvette that allows you to put less and still maintain the same height. The height is important because you want the beam of light to pass through here. If this is half empty, then the beam of light will pass through air. So the height is important for your sample and the path of light, where the light is hitting your sample. Another procedural consideration is the selection of the wavelength. And if you remember from HPLC lab, we talked about selecting lambda max for quantification. Does anybody remember what is lambda max? I'm sure all of you remember what lambda max is. Nick? The wavelength at the highest absorbance. And why we want that? Because you have the maximum sensitivity there. So you can detect lower concentrations at the lambda max. And also at lambda max, you have a really slightly, what do you call, flat line here or band. What does that mean, the flat band here? That means some wavelengths, like let's say 344 and 355, gives you the same absorption. So you want to select at that peak, a wavelength at that peak. So if your filter is giving you, instead of 344, it's giving you 345, you still get the same sensitivity. So, but if you select here at somewhere like at 325, there is a steep change. So 335 versus 336 might be very different in absorptivity. So you don't want to select here. That's why not only for maximum sensitivity, it's also for greater adherence to Beer's law. That means you select at an area where wavelengths are going to give you really similar absorptivity. So if your filter is slightly wide and is allowing a couple of wavelengths to go through, but they're going to give you very similar absorptivity, then you can have adherence to Beer's law. I don't know if that is clear to everybody. If it's not clear, I'm happy to repeat. Okay, assume everybody's clear on that. Okay. Another thing we do is we calibrate the instrument, 0% transmittance and 100% transmittance. That is, before we put the sample, we just want to make sure that it is calibrated where the beam of light is completely blocked. So there is no light going through, so we block the source of light and we calibrate it at 0% transmittance. And then we open it up and allow it to go through the cell and say this is 100% transmission. Another important thing for Beer's law is to select a range where you have linear relationship between absorption and concentration. And those of you that did, well, we all did the caffeine lab and some of you did the AA lab. So what happens is we select concentrations of our standards where we know that we're going to have a linear line, okay? So we select concentration of our standards so that absorption has a linear relationship with concentration. And then we dilute our samples to fit that standard curve. We shouldn't have a sample that reads at 10 or 12 molar or whatever that is, concentration, millimolar, because we don't know after this 10 if the line is going to curve or not. If it curves, like in this example, if it plateaus, this is not going to give you linear, obviously it's not linear, and this, you're not differentiating between 8 millimolar and 10 millimolar. It's plateauing. So we have to go back. For this analyte compared to this analyte, we have to prepare concentrations ranging from 0 to possibly 6 and plot the line again to get linear relationship. So depending on your analyte, the concentration you choose will be different. That will give you a linear relationship between absorption and concentration. And that was evident in the AA lab for calcium versus iron. You had different concentrations for calcium and different concentrations of iron to get a standard curve that has a linear equation of the line. So those of you that did not do the AA will see that next week in lab. So selecting the concentration is very important to get accurate results. Now this is a little bit complex, and I'll go over it as slow as I can. So basically here, if you have a complex sample matrix, you will not be able to prepare your standards in solutions that are exactly the same as your sample without your analyte. It's almost impossible to be able to prepare a blank and standard solution that has all the components your sample has except the analyte. In this case, we do a unique way of calibration, and we call it addition protocol, a standard addition protocol calibration. In this case, we use the sample matrix for developing a standard curve. I'm going to draw this out. So let's say you want to prepare a standard curve with 5 different standard concentrations. So you have your volumetric flasks where you're going to prepare your samples, dilute your samples, and also prepare your standards. So in all of them, you add the same amount of your unknown, volume of unknown, the same amount. And then what you add here is the volume of your standard, but in each flask, they get different volume of a stock standard solution. So let's say 10, 15, 20, 25, 35 milliliters. Okay, so you are building a standard curve within your sample, and then you dilute up to the same volume, say 100 milliliter with whatever, buffer or water or whatever it is. So now you know the concentration of your standard in each. You know the amount of sample you added in each. So what you can do is you can plot. You'll plot absorbance over the volume of the standard that you used. You have used 5 different volumes. Then you have an equation of the line. The equation of the line, you have a constant, which is the path length multiplied by absorptivity. And then you have the volume of the standard. You have the volume of the unknown. You have the concentration of the standard. What you need, what you will solve for is a concentration of the unknown. And then this is how you get your concentration. So it's a little bit more complex, but the idea is to have a same matrix in your standard as in your sample. To account for any interference from the matrix of the sample. Luna, how can I help you? Are you good? Okay. All right. There is indiscriminant error, or in other words, instrument noise. And the noise should be proportionally small compared to the actual absorption or fluorescence of your sample. So it should be less than 10%. Anywhere between 1 and 5% would be great, so that you can differentiate between the noise and between the actual absorption of your sample. So this error has to be small relative to the variation from sample prep, sampling, reagents, handling, analyst, etc. So this error should be smaller regarding, so that you can detect variation. We can determine the noise by testing the same sample multiple times in order to determine the instrument noise for that particular sample. And it can be reduced by the use of intermediate concentration. So this is very important. So when you prepare a sample and you measure absorption, and if absorption reads as 2, this is really high. And you are losing linearity, you have lots of noise associated with it. You really want to go back and dilute your samples or standards to make sure that absorption is between 0.2 and 0.8. That's kind of the ideal absorption, between 0.2 and 0.8. Some instruments are sophisticated. You can get an absorption of 1.5, for example, but you still can get low noise. Depending on how old is your spectrophotometer and the make of the spectrophotometer, the noise could be small even at higher absorptions. So, but something to keep in mind when you're running an experiment and you have really high absorption, you might want to think about diluting your sample to reduce the noise and the error and enhance linearity. Okay, instrumentation. So what's inside a spectrophotometer? There are very important components. Obviously, you want a light source, so you want your lamp. And for UV, it's deuterium lamp. For visible light, it's tungsten. And what happens is you have the light projected into a monochromator. And we talked about monochromator before, is when your light gets diffracted using a grating system, and then the light is broken down into multiple wavelengths, and then the filter that is there, it allows the exit of a particular wavelength. So this can be moved for different experiments to allow absorption at different wavelengths. So then the only light with a singular or very close wavelength exit that slit and goes on to towards your sample. So now only a select light with a select wavelength goes through the sample compartment. Absorption, reflection, the scattering occurs, and then transmitted light goes towards the detector. So what we are detecting in absorption chromatography, in absorption spectroscopy, is we are detecting the transmitted light. So we have types of detectors, phototube and photomultiplier. In AA, we had the photomultiplier tube detector for the atomic absorption. So a phototube, so here what you have is you have your cathode and you have an anode. So the transmitted light or the radiation beam is going to go in and hit the cathode. An electron is going to be emitted and it's going to hit the anode, and a signal is going to be generated. And that signal will go to readout. But the photomultiplier tube has enhanced sensitivity. Why? What happens from its name, multiplier, is actually multiplying the signal. How it happens is the light hits your cathode, and then there's your cathode, there's your anode. But when the light hits the cathode, an electron is transmitted, but it doesn't go to your anode directly. It goes to dinode, another dinode where you have more electrons emitted, and another dinode, you are multiplying the electrons that are emitted. By the time they reach your anode, you have really amplified the signal. Instead of one electron reaching, you are getting 27 electrons. So you're really amplifying your sensitivity, and you can detect at much lower concentrations. So this, like I said, the photomultiplier tube is the type of detector present in the atomic absorption. So when in a test I ask you what type of detector is in your atomic absorption, I expect all of you to know. Okay. Another type of detector is a photodiode detector. We talked about it. We have it in the HPLC lab, the PDA detector, photodiode array detector. So this is a powerful detector in such a way that it gives you your scan. It gives you the spectra. And how it functions is the light hits directly the sample. There is no filter here. So all of the light goes into the sample. And the sample absorbs light at different wavelengths. And then transmitted light goes into a monochromator. So the monochromator is here in this case, after absorption. Then it's not a monochromator. Scratch that. I am really tired today. It's a photodiode array. So this is an array of diodes. An array of diodes, so the light will hit an array of diodes, and then each wavelength is going to be transmitted as an electric signal separately into the detector, and you get a readout. And that's why we get a scan. So there's no monochromator, I'm sorry. There is photodiode array detector where all of the light at all wavelengths reach the detector. So instrument design, we have a single beam or a double beam. With that, what it means, if you have a single beam, that means there is a place, only one holding place. So you can put your blank, 0, take the blank out, and then put your sample and read. So when you have a single beam, what you need to do is you want to measure your blank multiple times during your analysis, because if it's taking half an hour to measure absorption of all your sample, there will be a shift and a drift. So you really need to measure the reference multiple times. Double beam is more efficient in terms of having two places. One, you put your sample, two two sample holders. One you put your sample and one you put your reference, which is the blank. And the lamp source gets split. So part of the beam goes to the sample and part of the beam goes to your reference. And then you get readout simultaneously and get subtracted for you simultaneously. So instead of zeroing or subtracting yourself, the instrument does it for you. The only disadvantage is your beam will become dimmer because you are actually splitting it. So the radiant power diminishes, which impacts sensitivity as well. So here's an example table where it shows the different chromophores. You have different structures that absorb light. And example component of a conjugated system or an aromatic or a non-conjugated system. You have different examples. It's showing you the lambda max for each one, the absorptivity, and then these are the references. So some of the compounds and functional groups, we already know their lambda max and already know their absorptivity by experimentation. Of course, you are supposed to know all of this for the test. No, just an example. Okay, fluorescence spectroscopy is similar with a little bit of a shift in the makeup of the instrument. So you do have a radiation source. You do have a monochromator, we call it the wavelength isolator, which selects the wavelength at which you're going to excite your sample. And then you have the transmitted light, which we don't measure. Okay? That's the question, the first question in the lecture. We do not measure transmitted light in both absorption and fluorescence spectroscopy. So incident beam, transmitted, we don't measure that. At a 90-degree angle, we project the emitted light. That means the fluorescence. And it goes through another monochromator or wavelength isolator. So we have an excitation wavelength and we have an emission wavelength that we are going to measure at. So we select the excitation wavelength and then we select the emission wavelength to be analyzed. So when we set up to measure fluorescence, we always have to set up two lambdas, one for excitation and one for emission. Okay, I'm done with this. Zach, what should we do? You know what we should. No, that wasn't the answer. We should redo the recap questions. There it is. No, it didn't work this time. All right. I think we did the first 3 last time. Right? Did we answer this? How does the wavelength impact the frequency and energy? We didn't. How does the wavelength impact frequency and energy? So compare a short wavelength versus a high wavelength. Yeah, go ahead.
So a short wavelength would have a high frequency and energy, while the opposite is true for a long wavelength.
Thank you, Nico. Yes. So with the shorter the wavelengths, you have more oscillations per unit time, so you have more frequency, and with more frequency, you have more energy. Okay? So that's why the incident beam or the excitation energy has higher frequency, shorter wavelength than the emitted energy after excitation, going back to ground state. You will have longer wavelength, less frequency, and less energy. What is Beer's law? Without looking, yes, it's the relationship between absorption and concentration, and it is a linear relationship. Okay. Why absorbed light is, and then when if and when I ask this in a test, I would like you to state that statement and write the equation, absorption equal ABC, and explain what these are. Okay. Why absorbed light is not equal incident beam minus transmitted light? That's again part of the beginning of the lecture. Why we can't subtract the incoming light or the exit light from the incoming light and call it absorption? Yes, Riley? Yes, because there is reflection and there's scattering, so not everything is absorbed and not everything is transmitted. Zach, what should we do? Yeah. Okay.